Log on, tune in, find out. Another good idea from Cambridge.
Next talk, it's a pleasure for me to introduce you Carine Jauberthie from LAAS in Toulouse in France. LAAS means Laboratoire d'analyse et d'architecture des systèmes, which means the laboratory of systems analysis and architectures.
Thank you for this invitation. Now, in this talk, I'll give. Sorry? Yes. Like this? Yes? Okay. I'll give some details on the methodology of optimal input design for aircraft parameter estimation, and I'll give an example of application. Now, this is the outline of my talk. In the first part, I briefly introduce the optimal input design for aircraft parameter estimation. I'll give the aims and principle. After this, I'll develop the methodology of optimal input design. I'll apply it to an example, and I conclude. This example describes the longitudinal motion of an aircraft in classical atmosphere. Now, the systems considered in my talk are nonlinear dynamical controlled systems given by this, by this classical form, where the functions f and g are nonlinear. The parameters to be optimized are given in red color, P, here, and the input to be optimized is given by U, here. We suppose we have some initial conditions given here. The measures are given by these equalities. In these equalities, P bar is supposed to be the true value of the parameters, and the variable nu on Ti are supposed white Gaussian noise random vector with zero mean and a covariance matrix which is known in diagonal. The number n here represents the total number of sample times. In aerospace, we suppose we have some realistic practical constraints given by these two inequalities, constraint here on inputs and here on outputs. Thus, the optimal input design for me consists in selecting the most interesting experimental conditions in order to obtain simultaneously the most relevant information with respect to parameters and the respects of the constraint set, the set on inputs and outputs. The aims are, the first here, to have an improvement of the accuracy level on estimation of the model parameters, and sometimes we would like to reduce the test number and we would like to reduce the test duration. In the presented work, I don't consider these 2 points. Now, this is the principles of the methodology. Firstly, we must choose a cost function, j of xi. In this talk, the variable xi represents the vector of experimental conditions to be optimized. Xi contains the inputs and not initial conditions here. Secondly, we must define the set of admissible inputs, noted E. And to finish, we optimize this cost function with respect to xi in E. Now we know that the cost function is a scalar function of information matrix of Fisher, noted here M function of P and xi. In my talk, the cost function is the trace of the inverse of M. You know that with the measurement noise, which are Gaussian, we have this expression for the matrix of Fisher, and the sensitivities given by these derivatives can be obtained by the solution of these systems or by finite differences. Now, the trouble is in the case of a nonlinear structure, which is my case, the optimal input depends on the values of the parameters to be estimated. Thus, a classical approach consists in fixing an initial parameter value, noted here P0. For the following example, this initial value can be obtained by wide tunnel measures. Now we can talk about the developed optimal input method. This method is divided into two steps. The first one consists in obtained by using the dynamic programming the first input, which is used as initial point to the second step. Now I can talk on the first step. We suppose in the first step that the time test is divided in two stages, like this one. Here, for example, here this is the time test. We suppose we have divided it into two stages. Thus, over each stage time, we suppose some possible constant control are applied. Here, for example, the constraint on input is given here. The input is in one dimension. We suppose we test ut equals to k, here equals to 0 or equal to minus k. And on the second stage, we test the same value. Then the consequences of each control possibilities are computed. Here, we computed the reconstruction of output. These outputs lead an initial condition for the second step. Now, this technique discards any input among square wave sequence whose output trajectory exceeds constraint limiters. And to finish, here we compute the cost function and we select the best input among these square wave inputs. Now, here we have an example of input obtained by the first step. Here the value is k. We know that this expression can describe this signal. And in this expression, the function h represents the Heaviside function. Now, more generally, if you work with m stages, the first steps consist in searching the most interesting input among square wave inputs given by this form. In this expression, the variable of input to be estimated are given in green color. This is the epsilon I, here and here. The constraint on epsilon I are given here. Epsilon I belongs to the set -1, 0, or +1. I remind here the cost function to optimize, and by using these steps, we obtain a first point of input noted xi hat 1. Now, in the second steps, we approach the previous function by this regular function given here. We know that when k tends to infinity, this input util tends to this one. Thus, in this input, the variable to optimize are given by ai and ti. ai represents the amplitude of square waves, and ti the switching time between two stages. By using an optimization method based on a gradient algorithm with initial point given by the previous input, we can obtain an optimal input. Now, an example of application of this approach. This example describes the longitudinal flight of an aircraft. In this example, the state variables are given by v, the speed of aircraft, alpha, the angle of attack, q, the pitch rate, and zeta, the angle rate. The parameters to be optimized are given in red color here, given by CZ alpha point, CMQ, CM alpha point, and CZQ. CZQ is here. The input to be designed is given by delta M here. Delta M represents the elevator deflection angle. Now, this research was conducted at the Onera Center of Lille. Thus, the experiments are based on 3 flights of scaled models in a laboratory at the Onera. And to these experiments, we work with 4 stages. We suppose the initial conditions are known and the time duration of experiments is given by 1 second. Thus, for 4 stages, we must test this input. In 1 second of test, the variable T0, T1, T1, T2, T3 are given here. And I suppose I have a constraint on the amplitude of square wave, A. A must be belongs between minus 1.6 degrees and plus 1.6 degrees. Thus, by using the first step of the methodology, by using the dynamic programming principle, I obtain this input. In the second step, this input U1 at is approximated by another input, by this one. Here, I give k equals to 100. I have this constraint on amplitude and switching time. And by using the previous methodology, we obtain this xi hat. Thus, on this figure, on the left part here, this is the results obtained by the first step of the methodology. And on the right side, the optimal input. Here, the optimal input. Here, the first input. Here, this is the reconstruction of outputs. The speed, angle of attack, pitch rate, and here pitch angle. Now, here, the regular function obtained by the gradient algorithm. Thus, some value for the criterion, for the trace of the inverse of matrix. Here, in the first column, this is the obtained input by step 1, by using dynamic programming principle. The input 2 is the optimal input obtained by step 2. By input 3, it means the input obtained by the square waves input obtained was parameters are obtained by step 2. And in input 4, the input 4 is a non-optimal classical input. In this table, we can see that the input 2 gives the smallest value. Sorry. Now, some result on estimation. Now, this is the relative error on estimated parameters. Thus, the criterion to optimize is a least square classical criterion. In the first column, the ponderation, the weighting matrix is obtained by the inverse of the covariance matrix of the measurement noise. And for the second column, the weighting matrix is obtained by a more sophisticated formulation. It is called by a formulation by using linear matrix inequalities. The using of linear matrix inequalities leads to improve the conditioning of the estimation problem. Thus, we can see that the optimal input and the classical least square criterion leads to the best values. for all parameters CZ alpha point, CZQ, CM alpha point, and CMQ. Now, to conclude, on the first part of this talk, I can say that the optimal input design in 2 steps lead a good improvement on criterion values and on accuracy estimation of the model parameters. This result can be obtained with a reasonable computation requirement, which is not the case when you use just dynamic programming principles. Now, my recent developments concern the optimal input design for systems with bounded uncertainty. In this work, the optimal input design are the same aims that the previous approach, but I would like to obtain an optimal input for a possible interval of parameters. In this case, we consider the case of uncertain systems, and in these systems, it's a little bit different than previously. The little p in red color is supposed to be a point in a priori box. By box, I mean a Cartesian product of intervals. And here, the initial conditions are not punctual conditions, but belongs to an a priori box. In this case, for this kind of models, the matrix of Fisher is not a matrix with points, but an interval matrix. An interval matrix is a matrix whose components are all interval. Thus, the trouble with these uncertain systems and this matrix is that the determinant of this matrix interval is an interval, and this interval contains 0. Thus, this matrix is not invertible. Thus, the criterion to be optimized to obtain an optimal input is not the trace of the inverse of matrix, but the determinant of M. But in the case of uncertain systems, is it possible to let this problem as a maximin optimization given by this form? By this form, and by using the first step of the previous methodology, the steps based on programming principle, we can obtain an optimal input, and I have no numerical result today, but we have obtained some first encouraging results for the previous example, the longitudinal flight of the aircraft. Now, some references. Probably I forget someone. I'm sorry.
Time for questions. Does your talk concern only simulations, or have you tested it on a mock-up at least?
Yeah, is it simulation? But there is a software which is implementing this method. It's a software Onera. And this software is used in real life.
Must be very difficult to implement, because you must take a lot of constraints into account due to safety reasons when you have a plane, especially constraints on angular velocities.
Yes, it was, but
Otherwise, well, it may fall very rapidly.
It was not very difficult to take into account these constraints.
You had 3 possibilities regarding
for the
control,
first
but have you tried to test it for a greater number of design levels?
No.
Because dynamic programming is very
very time consuming.
Yes, the computational burden is.
Yes, and this is why I test the 3 input. This one. This is a square wave. In this input, the parameters of these inputs are obtained by the step 2, and it will be better than this one. This is a trade-off, but in real life, this input by step 1 cannot be obtained. It's more precisely valued.
Great. That's a very fine application of dynamic programming and experimental design. Thank you very much once again.